In the previous video, we derived a formula for raising a complex number to the nth power, where essentially the magnitude of that complex number is raised to the nth power. It is multiplied by itself n times, and its angle is multiplied by n, or it's added to itself n times. And when our complex number is expressed in its polar form here, and we're raising that polar form to the nth power, this is equal to the right-hand side here, and we often call this de Moivre's theorem or formula, and I apologize if I am mispronouncing that. And for this video, I'd like to look at an example problem that actually uses this formula. And let's say we have the complex number, we can call it z1 as 1 plus I, and it will be useful to rewrite this complex number in its polar form, since we are going to take z1 and raise it to the 8th power. Now remember the formula for a complex number in its polar form. We need its magnitude and its direction. And the magnitude of the complex number can be expressed as the square root of the real part squared plus the imaginary part squared. And its angle, theta, is the inverse tangent of the imaginary part divided by the real part. And of course, if we want, we can plot this on the complex plane. It would be right here, draw a line, and then we can draw a right triangle if we want to figure out this angle theta and its magnitude using the Pythagorean theorem. But these formulas essentially do all of that for us. So we can plug in what we know into our formulas. We essentially have 1 for both our real part and our imaginary part. So the magnitude of our complex number z1 is the square root of 1 squared plus 1 squared, which is the square root of 2. And its angle is the inverse tangent of 1 divided by 1, or the inverse tangent of 1, which if you evaluate this on a calculator, you get 45 degrees. But this should make sense because when we plot this, again, on this complex plane, it would essentially split the first quadrant between the real axes and the imaginary axes. So the angle on either side of this is 45 degrees. And you get that anytime your real and imaginary part are the same size. So if it's 2 plus 2i, 3 plus 3i, and they're in the first quadrant, that angle is always going to be 45 degrees. And once we know its magnitude and direction, we can rewrite z1 in its polar form, since it's equal to the magnitude of z1, which is the square root of 2, multiplied by the cosine of the angle plus I times by the sine of the angle. And we can now apply this formula where we are raising this complex number to the 8th power. So we will take our magnitude and raise that to the 8th power, and we will take our direction, this angle, and multiply it by 8. So we have the cosine of 8 times by 45 degrees plus I, let me make a little bit of room, plus I times by the sine of 8 times by 45 degrees. I need just a bit more space. And we can simplify everything. If we look at this magnitude, we can rearrange this as the square root of 2 squared, and then all of that to the 4th power. It makes the arithmetic a little bit easier. And then we have the cosine of 8 times by 45. Well, 2 times 45 is 90, and then if we multiply 90 by 4, which is the same as 8 times 45, we get back 360. So this will bring us back to the positive real number axes, and we get plus I times by the sine of 360. And the square root of 2 squared is just 2. So we have 2 to the 4th power, which is 16. So we get 16 multiplied by the cosine of 360, or the cosine of 0, since 360 and 0 are the same angle. And if we want, we can now simplify this back to its rectangular form. since the cosine of 0 is just 1 and the sine of 0 is 0. So this is just equal to 16. And in conclusion, when we take this complex number, 1 plus I, and we raise it to the 8th power, this is just equal to 16. And another way to look at this, which we will consider further in a later video, is that if we take the 8th root of 16, one of the solutions is 1 plus I. And in fact, there are 8 different solutions. And what we'll see is that if we were to plot these solutions on the complex plane, that they are all evenly spaced in a circle around this complex plane. 1 plus I being 1, but also the square root of 2 times I. We have these points right here where all of these points are the square root of 2 away from the origin, but there would be 8 different solutions. We also know another solution to this is just the real value, the square root of 2, since when we raise this to the 8th power, we saw that that's just equal to 16. So there are 8 different roots of this number 16, and they were all equally spaced, essentially in a circle, around the origin here on the complex plane. But like I mentioned, we will explore this further in a later video.